Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list published on September 3rd, 2025, about 3 days ago. The big result is a video diffusion transformer that predicts true high dynamic range environment maps from casual images or videos, delivering accurate direction, intensity, and crisp angular details, with a 45% reduction on Laval outdoor sunlight direction metrics and nearly 50% lower peak angular error on direct sun scenes. The paper is titled LuxDiT, Lighting Estimation with Video Diffusion Transformer, and as we will see later, the results are really impressive. The method combines synthetic pre-training with low-rank adaptation to real panoramas, yielding temporally consistent lighting for convincing virtual object insertion and rendering. On X, posts describe LuxDiT as a diffusion transformer, estimating realistic high dynamic range lighting from images or video, outperforming current methods with detailed panoramas. Engagement shows moderate interest, around 170 likes. The previous segment highlighted the main gains and where they matter. Figure 1 shows the end-to-end promise. Input images on the left, predicted high dynamic range panoramas with shaded spheres in the middle, and virtual object insertions on the right. The middle panels communicate true lighting, because the chrome and diffuse spheres reveal direction and intensity. The right panels demonstrate scene consistency, so inserted objects cast plausible highlights and shadows that match the environment. So the previous figure established the goals and outputs. Figure 2 shows the core pipeline. The model predicts two tone-mapped environment maps, ELDR and ELOG, plus a directional map that encodes ray directions, which together capture true high dynamic range detail. A variational autoencoder embeds these into latents, which are concatenated with input image or video tokens and processed by a diffusion transformer. The decoded ELDR and ELOG are then fused by a lightweight mixer to reconstruct the final panorama. Alright, the previous figure outlined the pipeline components. Table 1 compares methods across 3 datasets using scale invariant RMSE, angular error, and normalized RMSE, which together capture intensity accuracy, light direction, and overall reconstruction quality. The bolded rows show consistent gains. The method achieves the lowest errors on Laval Outdoor and Polyhaven, and matches or beats competitors on Laval Indoor despite no training on that set. These improvements matter because lower angular error means more accurate sun direction, so shadows and highlights align in renderings. So, Table 3 reports video results, which matter because stability across frames is crucial for believable lighting. The table shows lower is better metrics, peak angular error on Polyhaven peak, and angular error on WEB 360 plus their standard deviations. Diffusion light lags with higher errors, while the image version improves markedly. The video model delivers the best scores, with 5.21 peak angular error and 1.95 standard deviation, and 5.218 angular error, with just 0.072 standard deviation, indicating much steadier predictions over time. Okay, the previous table quantified stability over time. Figure 4 presents virtual object insertion, which tests whether predicted lighting makes composites look believable. The columns compare reference, style light, diffusion light, DIPIR, and our method across 2 scenes so differences in highlight placement and shadow color become obvious. The rightmost column shows crisper, specular highlights on metal and more plausible soft shadows on the car, which indicate better sun direction and intensity. These cues matter because viewers judge realism from such small lighting agreements. Alright, 2 takeaways stand out. The video diffusion transformer delivers true high dynamic range panoramas with accurate sun direction and crisp angular detail, and the synthetic pre-training plus low-rank adaptation unlocks strong generalization and temporal stability. The broader impact is faster, more believable AR, and rendering from casual footage. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.